previous lecture we were discussing the time evolution of the coherent state. So, as we said that the coherent state were the eigenkets of the operator A, and we had shown that alpha can take any complex value. Just for the sake of simplicity, we assumed alpha to be real, and we found that the normalized eigenket was equal to e to the power of minus half alpha square summed alpha to the power of n factorial ket n. Then we said that let the harmonic oscillator at t equal to 0 be in this state, t equal to 0, let us suppose it is in the coherent state. Then how will this state evolve with time? And the answer is that if this is the state at t equal to 0, then psi of t at time t will be equal to, since these are the eigenkets of the operator h, e to the power of minus half alpha square summation alpha to the power of n factorial e to the power of minus I n plus half omega t ket n. The above equation, this equation describes the time evolution of the coherent state. Now, for this state we wanted to we calculated what is the expectation value of x and what would be the expectation value of p. For that we expressed x as a sum of a plus a bar, and similarly for p we expressed this as equal to something multiplied by a minus a bar. Then we evaluated the matrix elements, that is we evaluated psi of t x psi of t, and similarly we evaluated the expectation value of p, and we finally got the following results, that x was equal to x, which is defined as equal to psi of t x psi of t, this we showed equal to x naught cos omega t, where x naught was equal to 2 alpha times h cross by 2 mu omega. Thus, from this expression one can write down that alpha will be equal to mu omega by 2 h cross x naught. This is the eigenvalue of the operator A. Then we calculated the expectation value of P and we found that this was equal to minus mu omega x naught sin omega t. When we compared this equation with this, we found that this was equal to mu by dt of. So, the expectation values obeyed the classical equations of motion, So, this as we know is the Ehrenfest's theorem, that the expectation values observed follow the classical set of equations. Now, I leave as an exercise that if alpha was a complex quantity, if we had assumed alpha to be a complex quantity, we still would have obtained the same result, excepting that for x here instead of x naught we would have got a phase factor. I leave that as an exercise where the phase factor is such that alpha was equal to mod alpha e to the power of I phi. But this relation would have been valid, p is equal to mu d by dt x average, which is equal to minus mu omega x naught, but there will be a phase factor here. Except for the phase factor, all the analysis will remain the same. Now, as we go back to my previous slide, we ask ourselves that what is this coherent state? We say that the coherent state represents that of the classical oscillator. So, it is the superposition of the eigenstates of the Hamiltonian. Then we ask ourselves, what is the typical n value? So, for that we have to calculate for this the expectation. You see, we wrote down that ket alpha was equal to C n ket n, where C n is equal to e to the power of minus half alpha square alpha to the power of n by square root of n factorial. So, mod C n square represents the probability of finding it in the nth state. So, the classical oscillator is not in a particular energy state, it is in a superposition of a very large number of states, and that is what I want to make you understand. What are the numbers that are involved? How many states get excited? Is that just one energy state? No, it is the superposition of states. It is a superposition of states, and the probability of finding in the nth state is mod C n square. So, how many number of states are get excited? So, we calculate the average value of n that gets excited. So, we of course, from here you can immediately show that mod C n square is of course 1, because the state has to be found in one particular, the system has to be found in one particular state. So, you can immediately sum this. Mod C n square is e to the power of minus alpha square, and this will be alpha to the power of square root of n factorial alpha to the power of so, if you square this, so alpha to the power of n multiplied by n factorial. So, this is alpha to the power of 2 n by n factorial. So, that is e to the power of alpha square. So, that is 1. So, mod C n square is 1, and mod C n square represents the probability of finding, if the system is in the coherent state, the probability of finding it in the nth state. What is the typical value of n? Let me calculate the average value of n. So, the average value of n will be just n mod C n square. So, if I substitute that, so this will be n, and I can take the alpha square outside. So, e to the power of n alpha to the power of 2 n by n factorial multiplied by e to the power of minus alpha square. So, this is n divided by n, the first term is 0, because n equal to 0, this will be 0. So, this will be n equal to 1 to infinity. So, I write down this as e to the power of minus alpha square summation n equal to 1 to infinity, and if I write this down as alpha 2 to n minus 1. So, there will be alpha square outside. So, n minus 1 factorial. So, this is just, I can write n minus 1 equal to m. So, this is just e to the power of alpha square. So, this term cancels out with this term, and you will get finally the result that alpha square. I leave it as an exercise for you to show that. So, the expectation value of n is alpha square. Exactly the similar way you can show that expectation value of n square is alpha square plus alpha to the power of 4. So, the spread in n, that is equal to I can define this as n square minus n average square. So, n square is equal to alpha square plus alpha 4 minus n average square, that is alpha 4. So, this is equal to alpha, and therefore, this is equal to square root of n factorial. So, you have derived a very important result, and we will discuss the physical significance of that in a moment. So, we have the coherent state is equal to C n ket n. So, I ask myself the question, what are the states that are getting excited? The average value of n is alpha square, and the spread in the value of n is alpha. Now, we had the expression for x naught, as you recall, x naught was equal to alpha under root of 2 h cross by mu omega. So, alpha was equal to under root of mu omega by 2 h cross x naught. So, alpha square was equal to mu omega x naught square by 2 h cross. Let me take a classical oscillator of mass say 1 gram, a time period, the pendulum, the bob of the pendulum has a mass of about 1 gram. It has a time period of say 1 second. So, omega is equal to 2 pi by t. So, 2 pi second inverse. X naught is, let us suppose the amplitude is 2 centimeter, and h cross we know this is about 10 to the power of minus 27 erg second. So, alpha square becomes 1 into 2 pi into 2 pi square, 2 square is 4 into 10 to the power minus 27 into 2 into. If you work this out, it is approximately equal to 10 to the power of 28. So, the quantum numbers that we are thinking of, the average quantum number is 10 to the power of 28. You could have said that this, I could have told you immediately because the energy, if I write as n plus half h cross omega, then if I write E is equal to n plus half h cross omega, and I know that the classical energy of the oscillator is half mu omega square x naught square. So, if omega is equal to 1, then n, the approximate value of n, you say that the if this is equal to mu omega square x naught square by h cross, if n is very large compared to 1, h cross omega. And if you calculate this, you will find that this will be 10 to the power of 28. So, the quantum numbers that we are talking is a phenomenally large number. It is a phenomenally large number. But the other thing that I want to tell you is that how many states get excited. And if you calculate delta n, the spread in the value of n, that is alpha, which is about 10 to the power of 14. So, it is about 100 trillion states that get excited. But this number is extremely small. It is a trillionth, 100 trillionth of this number. So, please appreciate what I am trying to say. If this is n equal to 0, then this is n is equal to 10 to the power of 10 to the 28. Now, the energy levels are so closely spaced here that there are 10 to the power of 14, approximately 10 to the power of 14 states that get excited, but the energy levels are so closely spaced. What is the spacing of the energy levels? H cross omega. So, H cross is about 10 to the power of minus 27 ergs, and this is 2 pi hertz. So, this is the energy, this is a very small amount of energy. So, although the quantum number involved is large, this is my classical oscillator. Does it correspond to a fixed energy? No, it does not. It corresponds to a 100 trillion number of superposition of 100 trillion states around the quantum number 10 to the power of 28. But the spread of energy is extremely small. Let me tell you one more thing. This is slightly difficult, but once you understand, then this is the Bohr's correspondence principle, that in the limit of large quantum numbers, the system behaves like a classical system. So, let me write down the expression for energy. Energy is equal to, let me write it down on a fresh page. E is equal to n plus half h cross omega. So, the expectation value of E is equal to the expectation value of n plus half. Of course, half will be very small in comparison to that, but even then this is the expectation value of E. What is the spread in the value of E? So, I say calculate E square. So, E square will be average value of, if I square this, n square plus n plus quarter h cross square omega square. So, this will be n square average plus n average plus quarter h cross square omega square. Now, I have just now shown that that the average value of n, was alpha square. So, E square, the spread in the energy will be E square minus E average whole square under the root. So, this will be, if I take the square root, E square will be n square plus n plus 1 by 4. Of course, 1 by 4 I can neglect, minus E average square minus n average square minus this square of that, that is plus minus 1 by 4 minus n, whole thing h cross square omega square. Then we have calculated that n was equal to alpha square and n square was equal to alpha 4 plus alpha square. I just substitute this and carry out, and you will find that this will be equal to delta. Finally, we will obtain delta E by average value of E will be equal to 1 over square root of n. So, this will come out to be the spread in the energy, the spread in the energy will come out to be something. So, if n is equal to 10 to the power of 28, then delta E by the expectation, the spread in the E will be about 10 to the power of minus 14. So, the spread in the energy is extremely small. The spread in the energy is extremely small. Let me give you what I am trying to explain. I have plotted here. You see, this is a coherent state for which the average value of n is 10. So, there are about 15 odd states which get excited, 15 discrete states, and the vertical lines, I hope you can see them. The vertical lines on this figure are the probabilities, and if you add them up, C1, C0 square plus C1 square plus C2 square plus C4, 3 so on, they will add up to 1. So, for example, for C10 square is about 0.12. So, there is a 12% probability it is in a superposed state, it does not correspond to a particular energy, there is a 12% chance that it will be in the n equal to 10th state. So, there is a certain spread. Now, when we have, let us suppose n equal to 100, then there is about the average value of n is 100, but the spread is around 10. The spread is around 10. On the other hand, if n is of the order of 10 to the power of 28, then the spread in the value of n is about 10 to the power of 14. So, that in this scale, if you plot, there will be a very thin line. The spread in the E is extremely small in comparison to the E. So, that is what a classical oscillator is. So, delta E by E is approximately very closely to square root of n, the average value of n, and if my average value of n is 10 to the power of 28, then this will come out to be 10 to the power of minus 14. I leave it as an exercise for you that we had calculated the average value of x. I suggest that you calculate the value of x square also, because x, if it is some quantity multiplied by a plus a bar, then x square will be the square of this quantity a plus a bar multiplied by a plus a bar. So, there will be 4 terms a plus a bar plus a bar a plus a bar a bar. It will be just a little complicated, but very straightforward. And then you calculate delta x, and that will be x square minus x average square under the root. And then you find that if you calculate delta x by del x naught, the amplitude of the classical oscillator, that will come out to be, that will also come out to be n. And similarly, delta p by p naught will also come out to be 1 over square root of n. Because these numbers are very large, so this was about 10 to the power of 14. So, this is about 10 to the power of minus 14. This is also 10 to the power of minus 14. So, for the classical oscillator, is the uncertainty principle valid? Of course, yes, the uncertainty principle is valid. There is an inherent uncertainty in the measurement of x as well as in the measurement of p. But delta x by x naught, if x naught is 2 centimeters, if x naught is 2 centimeters, then delta x is equal to 2 into 10 to the power of minus 14 centimeters. This is a very, very small number. So, this is the domain of classical mechanics, where the position can be determined to a fair amount of accuracy, because the value of the Planck's constant is extremely small. So, when you look at a classical oscillator and you have a simple pendulum which is oscillating back and forth, a simple oscillator which is back and forth, let us suppose the amplitude is 2 centimeters, the time period is 1 second. So, that the omega is equal to 2 pi second inverse. The mass of the oscillator is 1 gram, and then you ask yourself, what does my quantum mechanics tells us? This is a coherent state, this is a coherent state, it is a superposition of a very large number. How much large? 10 to the power of 14 states, superposition of a large number of energy states. But the quantum numbers which we are talking of very high quantum numbers, 10 to the power of 14 states in the vicinity of n equal to 10 to the power of 28. So, that the width of the energy is extremely small, That represents the quantum mechanical description of the harmonic oscillator, and that is why we spent so much of time in the studying the time evolution of the coherent state, which happens to be an eigenstate of the oscillator. So, with this we come to the end of the linear harmonic oscillator, where we have discussed the, let me summarize what we have all done in the theory of the linear harmonic oscillator. We started out with the fact that the Hamiltonian is p square by 2 mu plus half mu omega square x square. Our objective was to solve this eigenvalue equation h prime ket h prime. The only thing that we assumed was the commutation relation, that x p, the commutated x p is equal to x comma p is x p minus p x is equal to I h cross. Using, we then introduced two operators a and a bar. A was equal to mu omega x plus I p divided by square root of 2 mu h cross omega. And by doing operator algebra, which is due to Dirac, we found that the eigenkets are denoted by ket h n. This is equal to n plus half h cross omega ket n. and these form an complete set of orthonormal kets, that M n is equal to delta M n. If I represent the matrix H in terms of these base, taking these as the base vectors, then I will represent them in the form of a square matrix whose elements will be M H n. This is the m nth matrix element of the operator H, in which the base vectors are the eigenkets of H. And since these are eigenkets of H, this is a diagonal matrix, and you will have the E 0, that is half H cross omega, 3 halves H cross omega, 5 halves H cross omega, and the rest all these terms. This is the matrix representation of the Hamiltonian when the base vectors are given by ket n. Similarly, I can make a representation of A bar, X and P. So, these are the matrix representations of the operator H. Then what we did was we solved this eigenvalue equation A ket alpha is equal to the eigenkets of the operator alpha, which we call them as coherent state. And we studied the time evolution, that if let us suppose psi t equal to 0, if it was alpha, then how will it evolve with time? And we found that the for such a state the expectation value of time oscillated sinusoidally, if alpha is assumed to be real. If alpha is assumed to be complex, then this will be something like this. And then we also found that P is equal to minus mu d by plus mu d by dt x. This is the Ehrenfest's theorem. And then we applied these results to a classical oscillator, and we found that for a classical oscillator extremely large quantum numbers get excited with a very small spread, although the number of states that get excited is very large, but the spread is extremely small to the quantum number itself. And so, therefore, we can say in principle that the energy of the oscillator is very accurately determined. There is a spread in the energy, there is an uncertainty in the measurement of the position, and there is also an uncertainty in the measurement of momentum. So, that completes the harmonic oscillator. We now go over to the theory of angular momentum. The theory of angular momentum. Before we do that, what I would like to say is we will consider two operators alpha and beta which commute with each other. If two operators are such that alpha beta is equal to beta alpha, then we say that the operators commute, something like two square matrices commuting with each other. Now, let ket alpha prime be a eigenket of the operator alpha belonging to a non-degenerate eigenvalue alpha prime. So, alpha equal to alpha prime represents a non-degenerate state. That is, there is only one eigenvalue, only one eigenfunction belonging to that eigenvalue. Then we have that alpha beta, if I write this, alpha beta operating on ket alpha prime, this is equal to, because alpha and beta commute with each other, then beta alpha ket alpha prime but alpha operating on ket alpha prime is a number, alpha prime is a number. So, this is equal to beta alpha prime ket alpha prime, because ket alpha prime is an eigenket of the operator alpha, but this is a number. So, I can take it outside. So, I get alpha prime ket p, where ket p is defined to be equal to beta ket alpha prime. So, this is ket p, beta operating on ket alpha prime is ket p. So, you have alpha ket p is equal to this. So, we have found that if ket alpha prime is an eigenket of the operator alpha belonging to the eigenvalue alpha prime, then ket p, which is equal to beta ket alpha prime, is also an eigenket of the operator alpha belonging to the same eigenvalue alpha prime, but it is a non-degenerate state. So, therefore, ket p must be a multiple of ket alpha prime. So, beta alpha prime is equal to beta prime ket alpha prime. You must remember that here alpha prime, alpha is an operator, alpha prime is a number, because this is an eigenvalue equation. This is an eigenvalue equation, ket alpha prime is an eigenket of the operator alpha belonging to the eigenvalue alpha prime. So, alpha prime here is a number. Here alpha prime is, here alpha is an operator, and now once it is a number I can take it outside. This tells us that therefore, ket alpha prime is also an eigenket of the operator beta belonging to the eigenvalue beta prime. Thus, if you have two operators which commute, then the eigenket belonging to a non-degenerate state will be a simultaneous eigenket. I further assert that if alpha and beta are observables, then as we had said earlier, that if alpha is an observable, it must be represented by a real operator. So, its eigenvalues are real, its eigenkets form a complete set of functions, complete set of eigenkets, and if two operators commute, then there will be simultaneous complete set of simultaneous eigenkets. If you have difficulty in understanding, let me give you an example. Let me give you an example. Consider the 2 by 2 matrix 0 1 1 0, one matrix, say alpha here, and beta is equal to 1 0 0 1. Now, I leave as an exercise for you to show that alpha beta is equal to beta alpha. Now, alpha is a 2 by 2 matrix, alpha has two eigenvalues. This leads to lambda square is equal to 1. So, lambda is equal to plus minus 1, and we had done this before, that the two eigenkets are say 1 and 2. 1 is 1 over under root 2 1 1, 1 over under root 2 is just normalization, and the second eigenket is 1 over under root 2 1 minus 1. Now, this is an unit matrix. So, this is an this has degenerate eigenvalue. So, but these are eigenkets belonging to non-degenerate eigenvalue. This is for lambda equal to plus 1. This we had done before, so I am not doing it again. But if you have difficulty, you can immediately calculate the eigenvectors of this Hermitian matrix, and you will find that ket 1 and 2 are simultaneous eigenkets of alpha and beta. And because alpha beta is equal to beta alpha, and any vector like a b can always be represented as a linear combination of ket 1 plus ket 2. So, in the 2-dimensional space, they form a complete set of orthonormal vectors. These are orthonormal, that is bra 1 ket 1, this will be 1 over 2 1 1 1 1, this is 1, bra 1 ket 2, this will be 0, bra 2 ket 1 will be 0, and bra 2 ket 2 will be also 1. Now, let me take another example, that I consider say gamma a matrix which is 1 0 0 minus 1. And then we again consider beta is equal to 0 1 I am sorry 1 1 0 0. Beta is the same, but gamma is now different, and you can again show that gamma beta is equal to beta gamma. Now, there are two non-degenerate eigenvalues 1 and minus 1, 1 and minus 1. The eigenvectors the eigenvalues are lambda is equal to plus 1 and minus 1. These are the diagonal elements here, and you show that there are two eigenkets now 3 and 4 I write, one is 1 0 and the other is 0 1. These are the orthonormal eigenkets of gamma. Since gamma and beta commute, these are also eigenkets of the operator beta. So, now I have 3 matrices alpha which is equal to 0 1 1 0. Now, alpha commutes with beta, gamma commutes with beta, but alpha does not commute with beta. So, you can have simultaneous eigenkets of beta and gamma, you can have simultaneous eigenkets of alpha and beta, but you will never have simultaneous eigenkets of alpha and gamma. It is as if that you are two people there, you both do not are not friend, I am friendly to you, I am friendly to you. So, this beta matrix commutes with both of them. So, you can have simultaneous eigenkets of beta and gamma, beta commutes with alpha, you can have simultaneous eigenkets of beta and alpha, but alpha does not commute with gamma. So, therefore, you cannot have simultaneous eigenkets of alpha and gamma. Let me conclude this. Actually, the matrices that we are considering are known as Pauli spin matrices. Some of you may have heard this. The Pauli spin matrices are sigma x is equal to 0 1 1 0, sigma y is equal to 0 minus I 0, and sigma z is equal to 1 0 0 minus 1. I would request all of you to play around with these matrices, and you show that of this the kets, the eigenkets, I represent this by say x, say 1 and 2, these are 1 1 and 1 minus 1 with the square root of 2. Of this, let me write it down with red, so that it, so this is, let us suppose, so of this we had said that ket 3 and ket 4 was 1 0 and 0 1, and here I think one of them is say ket 5, this is equal to 1 I square root of 2 and ket 6, 1 minus I, something like that. I would like you to confirm this. 1 2 3 4 I am sure, this is also I am sure, I am almost sure. First, 2 points that I, the unit matrix, say let me write down a matrix sigma which is equal to 1 0 0 1. Now, sigma commutes with sigma x, or let me just write it as sigma. Sigma commutes with sigma x, that is sigma sigma x is equal to sigma x sigma. Sigma commutes with sigma y, and sigma commutes with sigma z. Ket 1 and 2 are simultaneous eigenkets of sigma and sigma x. Ket 3 and 4 are simultaneous eigenkets of sigma and sigma z, and similarly ket 5 and 6 are eigenkets, simultaneous eigenkets of sigma and sigma y. So, sigma commute, but on the other hand sigma x does not commute with sigma y, and I leave this as an exercise for you to show that you can never have simultaneous eigenkets of sigma x and sigma y, you can never have simultaneous eigenkets of sigma x and sigma z, but you will always have simultaneous eigenkets of sigma x and sigma y. And one more thing that you must have noticed, that since these are this is degenerate eigenvalue, all eigenkets of sigma x are eigenkets of sigma, but since this is a degenerate case, all eigenkets of sigma are not eigenkets of sigma x. But in the 2-dimensional space you can always choose. In the case of degenerate states, a linear combination of the eigenvectors is also a possible eigenvector, we had shown that if you have a degenerate state, let us suppose I have an operator alpha and there are 2 eigenkets. So, alpha 1 is equal to alpha 1 alpha 1, and there is another ket alpha 2 which has the same eigenvalue. Then you multiply this by C 1 and you multiply this by C 2, and these C 1 and C 2 are numbers. So, you get alpha into C 1 alpha 1 plus C 2 alpha 2 is equal to alpha 1 C 1 alpha 1 plus C 2 alpha 2. So, this is also, this ket P is also an eigenket of the operator P alpha belonging to the same eigenvalue. So, for a degenerate state, if there are 2 linearly independent degenerate states, their linear combination is also an eigenket. So, in the case of this square matrix 1 0 0 1, there are 2 degenerate eigenvalues. Now, 1 0 is an eigenvector, 0 1 is an eigenvector, but the sum of the two, that is 1 1 is also an eigenvector. I hope I have been able to make you understand that when two observables commute, alpha beta is equal to beta alpha, you can always construct a simultaneous set of a complete set of simultaneous eigenvectors. Now, we go over to the theory of the angular momentum. When we had discussed just before we discussed the hydrogen atom problem, we defined the angular momentum vector as L is equal to R cross P. So, Lx was equal to y p z minus z p y, and then the other three are given by Lx, Ly, z p x minus x p z, and Lz is equal to x p y minus y p x. Now, we took over the same definitions, but now we will also assume the fact that x and p x do not commute. In fact, we had this relation that x comma p x was equal to I h cross, and similarly y comma p y is also equal to I h cross, and z comma p z is also equal to I h cross. But x and y commute, that is x comma y operating on psi on a wave function will be equal to x y psi minus psi x phi, sorry, x y psi minus y x psi. Now, both of them are equal. So, this is 0. So, x comma y or y comma z, they are all 0. Not only that, if I have x comma say p y, so this, as we had said, that if I represent this by a differential operator, so this will be x p y minus p y x operating on psi. So, this will be minus I h cross x delta psi by delta y, and since this is a partial differential with respect to x, y, x can be treated constant. So, this is x delta psi by delta y. So, this is 0. So, x comma p z is also 0, and similarly y comma p z is also 0, and y comma p y is also 0. Y comma p y is not 0, y comma p x is also 0. So, all the matrix elements, all the commutators are 0 excepting these three. In developing the formal theory of the angular momentum, we will just assume this, and we will derive using this that the commutator of Lx Ly, we will show that this will be equal to I h cross Lz, and similarly you can write them down in cyclic order. Ly Lz, this is equal to I h cross Lx, you can see this, and Lz Lx is equal to I h cross Ly. So, these are all in cyclic order, x y z, y z x, z x y, and obviously therefore, for example, Ly comma Lx will be equal, Ly comma Lx, sorry, Ly comma Lx will be minus sign of that. So, these are now in inverse cyclic order, IH cross Lz, Y, X, Z. So, one must remember this. We will also show that L square commutes with Lx and L square commutes with Ly and L square commutes with Lz. But Lx, Ly, Ly, Lz and Lz, Lx, they do not commute with themselves. So, therefore, you can have simultaneous eigenvectors of L square and Lx or of L square and Ly or of L square and Lz. So, in the next lecture, we will discuss the simultaneous eigenvectors of L square and Lz. Thank you.